welcome into this first lecture on differential equations in this virtual lecture series. Let's get right into it. This is going to be an introduction to the idea of differential equations, this first lecture. And so the first question that we should ask ourselves is, what is a differential equation? And I'm going to probably abbreviate. So what is a differential equation? And I'm going to abbreviate differential equation by DE for most of this lecture series. All right, well, it turns out that a differential equation is an equation that relates an unknown function with its derivatives. So an equation that relates an unknown function, which for the sake of this we'll call y, with its derivatives. And maybe not just its derivatives. It could be other functions of the independent variable. All right, so if the independent variable is x, then the equation could involve x's as well. So this is not a complete sentence, right? So this is called a differential equation. Now it's a little confusing because there are differentials which are different than derivatives, right? So this is not quite a differential. The differential equation is written in terms of derivatives, basically. So the derivatives of an unknown function. Our job is going to be to find that unknown function. So let me just first write some notation here. So one way that you could write a differential equation is you could have a function, some capital F here, that relates, say, the unknown, the independent variable t. So the independent variable is going to be either t or x usually, but we'll call it t for this one. And then the unknown function and some of its derivatives. And you can go up to as many derivatives as necessary. And then to make it an equation, you just set this whole thing equal to 0. So this is a very symbolic, heuristic way to write down a definition of a differential equation. We'll write down some examples in a moment, but some of the primary examples that we're going to study are first order differential equations. And I'll define this in a moment, but first order means that only the first derivative appears. So for us, a first order differential equation is going to be an equation that we can write as y prime, so the derivative, equals something in terms of just t and y on the right-hand side. So this is a function that relates just the t and the y on the right-hand side. And notice I've changed it from a capital F up here to a lowercase f down here, because the highest derivative is inside the function big F, but it's outside of the function little f, right? I solve for y prime down here. All right, so first order, we're going to study these extensively, especially at the beginning of the course. And then we're also going to spend a lot of time studying higher order, but especially second order. And second order, it's the same idea here, that you've got your second derivative now on the left-hand side, and you can write this as an equation that relates the second derivative to some combination, which is just what this function is doing, right? Combining somehow, some combination of the independent variable, the function itself, and its first derivative. So there's a typo. So it's first derivative here. All right, so that's the second order equation. So this leads us to another question, which is like, what can we define this word order, right? So when we classify our differential equations, there's going to be certain words that we use that we just have to know. So you'll have to know what these words mean. So first order of business here, pun intended, is to define what it means to be the order of a differential equation. So I'm just going to kind of make a list here. But the order of a differential equation is the highest derivative that shows up in the equation. So the highest or largest derivative in the equation. All right, so for example, if I were to write down an equation like, say, y4 plus 3ty triple prime minus 4t squared y prime equals log of y times t. All right, this is a differential equation because it's an equation that relates an unknown function here, y, with a bunch of its derivatives. There's no second derivative here, right? The function itself is mixed up over here on this side. We've got a y prime, triple prime, but the highest derivative is 4, right? So this is a fourth order equation. Okay. So that's how we're going to talk about these differential equations. The order is the highest derivative. Some other vocab that we need to know is the following. So linear. A linear differential equation is one for which the y terms can be written as linear combinations, as a linear combination with respect to functions of the t variable. So that's a really mouthful of stuff to say, right? But in this case, I'm going to write this down and then I'll write down an example. But the y terms, including the y derivative terms, right, can be expressed or can be written. I'm not saying this correctly here. So what I mean here is that the differential equation can be written as a linear combination of the y terms. So this is what I should have said. Sorry. The differential equation can be expressed as a linear combination of the y terms. And that includes the derivatives, right? Okay, so the way that we would write this down is we would write something like, our differential equation would look something like, say, alpha sub n of t. This can be a function of t times the nth derivative plus alpha n minus 1 times of t, so that's a function. All these alphas here are functions, times the n minus first derivative, all the way down to, say, alpha 2 of t, y double prime, plus alpha 1 of t, y prime, plus alpha 0 of t, y, equals, we'll say, some other function of t, g of t. And so the main idea here is that these y terms, right, all these y terms are not mixed up. They're not mixed up in functions themselves. So all these other coefficient terms are merely functions of t. So these are only functions of t. And so this is what it means to be. So all the green stuff that I just highlighted, those are just functions of t. And that's what it means to be linear. So, for example, we could write something like what I just wrote is that's a general formula, right? So that means our differential equation, if we can write it in this form, then it is linear. So linear combination. All right. So here's an example though. Let's say we have something like 3 y double prime plus 4t squared y prime minus natural log of t over t times y equals cosh of t squared. All right. There's a lot of functions here that are not linear functions. There's quadratic function here. There's a cosh function here, a hyperbolic cosine. There's a log divided by a t, so a log function and a kind of rational combination. But those all involve only the t variable. They do not involve the unknown dependent function y, right? So they don't involve y. And so this is linear. That's a linear differential equation. It's a second order. We can say that now too. Second order linear differential equation. A nonlinear equation is then one that cannot be written like this, right? So nonlinear just cannot be written as a linear DE. All right, so it's that simple, right? It's the opposite. If you cannot write your differential equation in this form, then it is not linear, and we call it nonlinear. So I'll just give you a simple example of this one. For example, here, this could just be something like y prime equals 3y squared. There you go. It's already not linear, right? Minus natural log of y prime. There you go. That's not linear, right? So in both of these cases, the problem is that the y is part of another function. So y squared, y times y. That's not linear, right? This one, it's natural log of y prime, so not linear. So this is a nonlinear. Definitely nonlinear. And this one is second order. Well, the way I wrote it's first order. I meant to write y double prime here. But it doesn't matter. So you can, even if that was y prime, it still would be nonlinear because there was a y prime also inside of this function over here, right? So those are both examples of nonlinear. All right, one last definition here that we're going to see throughout the semester is homogeneous, and we will see this mostly in once we get to chapter 3 and 4. But homogeneous, this is an important definition, so we'll state it now. A differential equation which could be called homogeneous is one that can be written in a way that we have all of the y's on one side, and then there's no terms that don't involve y. So in other words, up here, if this cosh of t squared was 0, then this would be homogeneous up here. This would be homogeneous if this term was 0. All right, so I'll write it out here. I'll try to write it out. But homogeneous differential equations can be written in such a way that no terms involve only t. Okay, it's kind of a hand-wavy definition, but we'll see exactly what this means as we move forward. But some typical examples are something like, say, y double prime minus 14y prime plus 6y equals 0. Notice there's no t's anywhere here, right? But so that's definitely homogeneous. But we could also do something like sine of t y prime minus natural log of t squared y equals 0. And so these are both homogeneous because they don't involve any terms that have only t's, right? So it's okay to have t's in these coefficients, but there's no term that has only t's. All right? So these are homogeneous differential equations. Okay, one more thing. Everything that I've talked about so far has been in relation to functions of one variable. So in other words, there's only one independent variable, and that has been t so far in everything that I've written down so far, right? So we'll write this down now. But differential equations that involve functions of just one variable, these are called ordinary differential equations. So functions of one independent variable these are ordinary. And ordinary differential equations are the only ones that we're going to study in this class. So you could call this class Ordinary Differential Equations 1 if you wanted to. But we will talk about, and you will see as you move forward in your life, what we call partial differential equations. And those are differential equations that involve functions of more than one variable. All right? So DE involving unknown functions of more than one variable, and derivatives of those, both variables or multiple variables. But I'll just write it this way for right now. More than one variable. These are called partial differential equations. Okay. So here's an example of a partial differential equation. This time I'm going to use a different letter altogether, but partial derivative of u with respect to x plus partial derivative of u with respect to t equals some function f of x and t. Something like this. This is a partial differential equation because the u, so the unknown function, u for unknown here, but the unknown function that's going to solve this differential equation has to be a function of x and t both itself. All right, so it's a function of two variables in this example. Okay, so that is a partial differential equation. All right, let's do an example of classifying a differential equation. So I'll write this down, call this item 2. But here's what I would like you to do. So classify the differential equation. Use all of the lingo that we just developed. So all those words that we just wrote down, go through and check off, what's its order? Is it linear? Is it nonlinear? Is it homogeneous? Is it ordinary? Or is it partial differential equation? So here's the differential equation that I'd like you to classify. It's y triple prime plus 3t squared y prime minus sine of natural log of t times y equals cosh of t squared again. Okay, so take a moment to pause and ponder this and classify this differential equation. All right, so now that you've had a chance to classify it yourself, hopefully you noticed that the order of this differential equation is the highest derivative, so that's on this one, right? So this is going to be a third order. Third order. It's an ordinary differential equation because there's only regular derivatives here, right? So I'll write this over here. Ordinary as opposed to partial, right? So ordinary, third order. It is linear, right? It's linear. So it's linear because these terms are not wrapped up in functions themselves. So this is a linear combination with respect to the y's, right? So third order linear, and it is not homogeneous. So I'm going to call that, and I mean, we didn't write this down, but if it's not homogeneous, then it's going to be non-homogeneous, which is probably not the right English way to say this. It would be like inhomogeneous, but this is the way the math people say it. So it's third order linear, non-homogeneous differential equation. All right. So there's a classification of this differential equation. All right, so the next item that we'd like to talk about is, okay, we now know how to classify differential equations. We kind of know what they are. Like if you look at it, you can see that it's a differential equation, right? But our job is going to be to solve these differential equations. So a solution, and this is our job is going to be to find a solution, right? That's what it means to solve. But a solution of a differential equation is a function, which I'm going to write. So let's just focus on ordinary differential equations right now, but you could this applies to partial as well. But I'm just going to write this as a function of a single variable, okay? So it's a function phi of t that satisfies, so when plugged in, it satisfies the dE. So the differential equation is written in terms of say y's, and then the function itself, the explicit function that solves it, is called a solution. And I said v, but there could be many, right? And there will be many. All right, so let's do an example together of just what I mean here. Here's a differential equation: t squared y double prime plus 5t times y prime plus 4y equals 0. And we have a condition here that t is greater than 0. So we're given this restriction. And notice just by looking at this differential equation, we can see that t equal to 0 is a problem because of this, right? And really this too. But if we were to allow t to be 0, then it would zero out some coefficients, and we would be left with something that's not a differential equation at all. Okay, if t is 0, then these are both gone, right? And then we're left with just 4y equals 0. The derivatives are gone. So we've set this criteria then, right? That t is not 0. It's greater than 0 in this case. And I want to show that this function, which I'll call phi1, because it turns out this has multiple solutions, but phi1 of t equal to t to the minus 2 power, that this is a solution. So what do I have to do? Well, I have to actually take the derivatives of this function phi1, and plug them back into this equation and make sure that the left-hand side truly does add up to 0, right? So I need to take these derivatives, and I'm going to write this out in kind of like a table. So I'm going to call this phi1 of t, right? This is equal to t to the minus 2 power. And then phi1 prime, take the derivative. So this is minus 2t to the minus 3 power. Right? So, and then phi1 double prime of t. This is going to be uh, 6t to the minus 4 power. All right. And so this is what needs to get plugged into our differential equation then. All right, so we just take these and we plug these in back up here. So I'll highlight and then we'll plug in. So this one's going to go in for where phi, or y, is, right? This one, all of this is going to go in where the derivative is, and then all of this goes in right here. All right, so let's see what we get. We end up with t squared times 6t to the minus 4 plus 5t times negative 2t to the minus 3 plus 4t to the minus 2. And we do not write equals 0. That's what we're checking, right? So now we just multiply all this out, and we see what we get. So I'm going to write this over here, but look what happens when we combine this. We have 6t to the minus 2, these combine, plus negative 10, so minus 10t to the minus 2 as well, negative 3 plus 1, and then plus 4t to the minus 2, and then we see that these coefficients do add up to 0, t to the minus 2, well that's just 0, right? And so this checks out. And so that's how we show that this phi1 is indeed a solution of that differential equation. Okay, here's another one for us to do together. This time, I'm going to give you a differential equation. So consider the following second order differential equation, second order linear differential equation. So this one's going to be y double prime plus 4y prime plus 3y equals 0. And I claim that that the solutions can be written in the following form. So here's the question. I'm going to write it in the form of a question. So for what values of r is the function phi equal to e to the rt, for what values is this a solution of this differential equation? All right, so take a minute, pause and ponder, see if you can figure this out for yourself, and then we'll do it together. Okay, now that you've had a second to work on this one, you have to do the same thing that we just did on the previous one, right? Which is to write down our potential solution here. We hope it's going to be a solution. And then take its derivatives, and we'll have to plug those in, right? So phi is e to the rt. Phi prime, r is going to be a number here, right? So the derivative of this is r, e to the rt. And phi double prime is r squared, e to the rt. R is just a number, so the derivatives are pretty straightforward. And then when we plug these into our differential equation, we get r squared e to the rt plus 4r e to the rt plus 3 e to the rt, and that's got to equal 0, right? We want this to equal 0. Now, what we notice is that these terms can all be factored out, e to the rt, and this will leave us with this equation. All right, and of course e to the rt itself can never be 0, right? E to the rt is a positive, it's a positive function, exponential function, so that can't be 0. So what we conclude then is that this quadratic equation must be satisfied, right? So r squared plus 4r plus 3 has to equal 0, and there are many ways to solve this. Factoring is probably the easiest, right? This factors to be r plus 3 times r plus 1. And so the values of r are minus 3 and minus 1. Okay, so those are the values of r for which this is a solution. So let's write the solutions down, right? So the solutions are, we get two solutions. So our two solutions are going to be phi1 is e to the minus 3t, and phi2 is going to be e to the just minus t, minus 1t. It doesn't matter how you label them, 1 or 2, but they're different, right? They're different functions. Okay, and so there you go. There's solutions to this differential equation. So now we know what differential equations are, at least, again, symbolically. We know how to classify them, and we know what it means to be a solution of a differential equation. We still haven't talked about how to find that solution ourselves. But one question that you're probably wondering is, how are these things useful, right? So why do I need to learn about differential equations? Well, differential equations show up in all kinds of physical applications. So in particular, DEs are used to model many physical phenomena. All right, because remember, derivatives measure rates of change, and so anything that can be thought of as a rate of change, which is many, many, many things in physics, can be written in terms of derivatives of some unknown function, and therefore combined to make differential equations. All right, so these are used to model physical phenomena, and we'll just look at one example here. And so I'm going to derive the equation of, so a differential equation that models a free-falling body near the surface of the Earth. All right, so free-falling body near Earth. And when I say near Earth, I mean like near the surface, like near the ground, right? Like an apple falling from a tree, if we want to channel Isaac Newton. And let's do that, right? So Isaac Newton, so here's the situation, right? You just have some object, an apple. It's falling down toward the Earth. So I'll draw a curved Earth here. Right? It's falling down towards the Earth. So Newton's second law tells us what? That the force, right? Force is equal to mass times acceleration of this object. So it's the mass of this object. This is an apple, so it has some mass, and it's got an acceleration downward. That acceleration is always the derivative of velocity, right, with respect to time. So we can write this down. So our A, we know, is derivative of velocity with respect to time. It's the rate of change of velocity with respect to time. That's the definition of acceleration. So what we end up with here is that we have a formula for the force exerted on this apple, we'll say, by the Earth is F equals mass times dV by dt. Okay, but we also know that since we're talking about being near the surface of the Earth, right, but the acceleration is given by gravity, right, in this case. So acceleration due to gravity near Earth, right? So acceleration is due to gravity near Earth, and this is the free-falling part. There's no other acceleration, so there's no motor on our apple. We didn't, there's no initial force on the apple, but gravity near Earth, remember that A is just, it's a constant. It's equal to G, which is about 9.81 meters per second squared, right? So that's the constant acceleration due to gravity pulling downward, which is the same direction that I've drawn the picture here, right? So there's the acceleration due to gravity. So F on one hand, we could replace this all with F equals mg. But also, if we're really close to the surface of the Earth, then we have to factor in the atmosphere, right? This is not just happening in space. They're in the vacuum. There's actually drag on this apple that's pulling it backwards, right? So the drag is pulling it this way, and the acceleration is pulling it this way. Well, we don't need to get into the physics of this, but the drag is proportional to the velocity. So the faster the object moves, the more the drag is going to try to pull it back, okay? So the drag is, I'll just write it right here, but the drag is equal to minus alpha times v for some constant alpha. And this constant alpha depends on the shape, it depends on the material, it depends on a lot of things, exactly what's happening in the air and the atmosphere, but it's a constant. So that's the idea. So this is the drag, and so we need to add this on to our equation here. So our equation now becomes mass times gravity, acceleration due to gravity, minus drag coefficient times the velocity. All right, but at this point, what we have is we have some equation for F up here that involves the derivative of velocity, and some equation down here that involves the velocity itself, right? For the same force exerted on the object, right? Same force F. So that must mean that these two equations or these two sides, the right-hand sides, are equal to each other, right? Just by the transitive property. And so we obtain, at this point, our differential equation. So this differential equation models free fall. Free fall near Earth, or like really close to Earth, right? Because we use these values well, we use G, and then we talked about the Earth's atmosphere, right? And what we get then is that M times dv dt is equal to m times g minus gamma times v. All right, and of course at this point we can divide through by m to make this a nice first order differential equation for v. All right, so we end up then with dv by dt equals acceleration due to gravity minus gamma over m, drag over mass, times v. And so this is a first order differential equation, FODA, right, for v. So in here, v is an unknown function of time, so velocity with respect to time. Okay, so this equation, it turns out, I'm going to write it down one more time, but this equation can be solved using Calculus 1 or Calculus 2 techniques, right? So I'll write it this way. We can solve this equation for v using Calc 1 or Calc 2 techniques. Really both, right? Calc 1 and Calc 2. All right, so I'll get us started and then I'm going to let you work on it. But one idea is that you can factor out some terms here and then you can separate this equation, okay? So you can take dv by dt, you can factor out the gamma over m. So you have this, and then honestly you can take out the negative gamma over m, and then you'll end up with v minus g in here, because I took out the minus sign, so you end up with this. All right, and so at this point you can separate. So remember how this works from Calc 2. This comes over here, right? And then what you'll want to do is divide this whole term down here. All right, so take a minute to pause and ponder this one, and we'll finish this off together in a moment. All right, now that you've had a moment to work it out, you should have ended up with an equation that looks like this, right? dv over v minus g equals negative gamma over m dt. And this is truly now a differential equation, because this, probably I should have written it even more clearly like this, right? 1 over v minus g dv equals negative gamma over m dt. Now we've got two differentials equal to each other. And remember, the differentials are things that you can integrate, right? From, calculus point of view. So we just wave our integral wand at these things, and we can integrate both sides. This ends up being natural log of v minus g, and this side is constant, right? Gamma and m are constants. So this ends up being minus gamma over m times t, and somewhere here we need an unknown constant, so I'll put it over here, plus c. Our job is to solve for v, though, so at this point we want to exponentiate both sides to get rid of the natural log, and then what we end up with is v minus g equals e to the, so this constant here, right, there's a plus sign here, right, so this can be written as e to the c, but e to the c is just some other constant. It's another unknown constant, right? So over here I should have like absolute value on this. I'll do it all correctly since this is the first lecture, but absolute value here, because technically the antiderivative is absolute value inside the log. This number here is always positive, right? So we can replace this then, and we can get rid of the absolute value and the e at the same time. But we can replace this by another unknown constant that's allowed to be negative, potentially, and that's how we'll get this all solved for. So v minus g is then equal to, we just replace this by a different unknown constant, but confusingly I'm going to call it by the same letter. And I'm doing this now because we're going to do it in the future, so we might as well get used to it. But this is then constant e to the minus gamma over m times t, and the last step is to add the gravitational force to the other side, right? So the function that determines the velocity of our falling object, our apple, in this case is equal to the force due to the acceleration due to gravity plus some constant e to the minus gamma over m times t. All right, and as time goes on, this term gets closer, right? Minus gamma over m. This is negative, and so as t gets very big, this term right here gets close to 0. So There you go. There is the solution of the free-falling body problem. Okay, so the last thing that we'd like to talk about in this first lecture of the class, of the course, is something called slope fields. So this is unique to what are called first-order differential equations. So let's say we consider a first-order differential equation. Remember, FODE or FODA. That's how I'm going to write down first-order differential equation, and we'll write it. Suppose that it's of the form, so it's already been written in the form y prime equals f of t y. All right, so f of t comma y. So in other words, it's solved for y prime. So example, right? Maybe it's y prime equals 2t minus y squared or something. All right, so there you go. There's a first order differential equation for y. In this case, how can we interpret this, right? So we'd like to interpret this geometrically. So geometrically, remember that the derivative represents the the derivative represents the slope, the instantaneous slope of the function, or the slope of the tangent line at every point, right? So y prime measures or represents the instantaneous slope of the unknown solution curve. So of the solution curve at each point. So at each point t comma y in the plane. All right, so what that means then is that a differential equation prescribes a slope, an instantaneous slope, so a slope for the tangent line at each point of our unknown function y. And what we can do then is we can plot tiny little line segments with the slope that's been prescribed at each point on the plane, and we can look at the way that those line segments change their direction, and we can then try to interpret the behavior of our solution by looking at that curve, or by looking at that what's called a slope field. Okay, so I'll just write it this way. But we can plot a slope field. This is called, in the book, it's called a direction field. To help understand the behavior of the solution without even knowing what the solution is, right? So, and really it's solutions. We'll see that they can have different behavior, the different solutions. So let's do a simple example by hand, and then I'll show you how to do this with a computer. As a first example, just like I said, very simple. I'm going to take kind of what we had on that previous example that I wrote down, but very simplify it a lot. So instead of 2t minus y squared, let's just do 2 minus y. All right? So at this point, we want to try to figure out what's the slope going to be at every point in the ty plane. Notice that the way that I've changed this, the right-hand side no longer depends on t, right? So this is just going to depend on the height, y. So let's plot a couple of heights. So 1, 2, 3, 4, 0, -1, -2. We don't want to get too crazy, but there we go. And then we'll just put some tick marks in the t direction. And let's see what happens, all right? So what I'm going to do is, again, it doesn't depend on the t, so we're just going to use these as a guide to help us plot this. But we're going to choose some values for y, and then we're going to write down our slope, y prime, our instantaneous slope. And we're going to use our function here, 2 minus y, to help us do that, right? So let's start up here with 4. So when y is 4, y prime is equal to -2, right? Well, -2 is like a steep negative slope like this. So I'll change this to red. But we just want to plot, these are all supposed to be the same slope, but line segments with the slope of -2, right? That are centered around all the points with y equal to 4. And that's it. So then we work our way down, right? When y is 3, y prime is equal to 2 minus 3, so -1. So that's still negative, but it's not quite as steep, right? It's not quite as steep. So it might look like this. Something like this. Try to keep all the slopes the same, right? And then we just keep on with this, and you can see how this is going to go, because y prime, these are just decreasing by 1 as I move, right? So this will be 0. Well, what's the slope of 0 look like? Well, that means that the curve has a horizontal tangent at these points. And look at this. Look what's going to happen. You can imagine now that that horizontal line itself, right? Because at every point with a height of 2, the slope is 0. So that horizontal line itself is going to be a solution. Okay, so y equals 2 itself is going to be a solution. And then we just work our way down. So when y is 1, y prime is now positive. So that's a positive slope, looks like this, positive 1. But it's going to look like a mirror image of what's right above it. I'm drawing this, so you have to bear with my drawing skills. But it looks like this, right? And then, well, I'll just do one more. But at 0, y prime is equal to 2. And then that's more steep, right? Well, probably not that steep, but more steep than that. And again, it should be like a mirror of exactly what's up here. So this is the idea. Now, how does this help us, right? So, well, there's a couple different things that we can notice. We already kind of noticed that this curve right here, so y equals 2, this horizontal line, this is going to be a solution. Because if we draw this curve, I keep saying curve, but if we draw that line, it is a curve, but we draw that curve, then it obeys the slope field, right? It agrees with the slope field at every point. Its slope is 0 at every point. Everything's good, right? And so this is called the equilibrium solution, because not only is it a line, right? This is called the equilibrium solution. So this is the equilibrium solution because this is the one which satisfies y prime equals 0. When we plug in y equals 2, y prime equals 0, so nothing's changing, right? The rate of change is 0, so that's why it's called the equilibrium solution. Now, your differential equations can have more than one equilibrium solution, potentially, but in this case, that's one of them. What about the rest of the solutions? Well, the rest of them, I mean, this one depends on being at a height of 2, right? So the rest of them are going to depend on the height and the t direction, to where you are in the t-plane. So let's say that that this slope field represents, forces or direction or something, and we drop a little marble, let's say right here. Okay, let me make it a different color so we can see it better. Drop a little marble, say right there. Then what do we have to do? We want to draw the curve that obeys this, right? This slope field. So it's got to have this slope at this point, but then the slope is going to gradually decrease or increase in this case to 0, right? It's going to become 0. And so this one's going to approach our equilibrium but never get there, right? Because it's never actually going to be able to touch 0. And then in the other direction, as it goes this way, it's going to decrease in this case, right? To become -2 and then beyond, right? And so there's the curve. Just by kind of imagining how this little marble would behave in our slope field, we can plot this little curve right here. All right, let's do one more. So let's say I drop a marble, say here, below the equilibrium in the y direction. So in this case, it's going to get, as we go to the left, it's going to get sucked this way, right? Kind of the opposite of that one. And as it comes to the right, it's going to get pulled toward the equilibrium. I'm sketching so it doesn't look great, right? But toward the equilibrium, and it's going to be the same kind of behavior. So this is going to be the look of these. Notice this equation looks a lot like I mean, there's actually numbers in this one, but it looks a lot like our example with the free-falling object, right? And the answer to that, the solution to that free-falling object problem was an exponential function. And these definitely look like exponential kind of curves, right? Okay, so this is how we can use geometry to help us interpret these first-order differential equations that we can draw the slope field for. So what I would like to do next is show you how to do this on a computer. Okay, so I have opened what's called, this is called Jupyter Lab, and I'm going to open SageMath here. I'll just do a console. So you can see down here, I'm going to type some commands, and we're going to get some output up here. You do not have to know how to do this for this class, but I am going to provide a link to a SageMath cell where you can play around with this code without actually having to download it yourself. All right, so the first thing that we want to do is try to replicate what we just did on the previous example. So for this one, I'm going to define the variables to be t and y, and then I'm going to define that function that was the right-hand side, right? So f prime equaled, y prime equaled 2 minus y. So that's what I'm going to call f, 2 minus y. All right, and then there is a nice built-in command. It's just called plot slope field. And if you start typing and press tab, it should help you finish, but it's not. So plot slope field. So we're going to plot the slope field for f, and we're going to plot this for t between, let's say, -5 and 5, and for y between, let's say, we did 0 to 2 in our chart, right? But let's say -2 to 4. And then you just run this command, and there you go. There's the slope field. So look at what we got. It doesn't have the exact horizontal, the horizontal line that we had, because it didn't actually plug in the height of 2, but it got really close, right? But you can see the shapes of these things are going to be very similar to what we had, all right? So that's the one that we just did. So let's change this up and make it slightly more complicated. So I'll call it F2 this time. And this time, let's take our previous one, which was 2 minus y, all right? And let's multiply another term by this, all right? Let's say we multiply this by, well, let's just do y minus 2, or let's do y plus 2, or 2 plus y. All right, so you can work this out. This would end up being 4 minus y squared, right? And in this case, we want to plot our slope field. Now it's working. So plot slope field. We're going to do this function f2, this differential equation. And again, let's do t from -5 to 5. But let's do the y. Let's go a little further this time. Let's go -4 to 4. I want to add a title to this one. And I'm just going to type out the differential equation here so we know what it is when it prints. All right. So it was y prime equals 2 minus y times 2 plus y, or y plus 2. It doesn't matter, right? I want this to look pretty, so I'm going to do something crazy to it. But let's do that. There we go. So there's the slope field. I'm going to save this and put this in the notebook, and we can draw on it. But there's the title, so it just making it look like the nice math font is all that those dollar signs and that little R did. But otherwise, we see we have the same equilibrium that we had before, right? And the behavior above that equilibrium too looks kind of the same. They get steep, right? And they're tending this way. But now we have another equilibrium down here, right? And then some crazy stuff's happening in between and below. So we'll print this one out and we'll look at this one on our own. But notice how that one would be a lot more complicated to plot by hand, even though it was just a simple change that we made. All right. Now, if we wanted to get real crazy, we can define a differential equation like maybe, so this should work for any first order differential equation, right? So let's do t, let's make a fraction, t plus y, all right, divided by e to the y. Okay, so t plus y divided by e to the y. I have no idea what this is going to do actually. So plot slope field again. We'll do f. Let's just do kind of the same window, but -5 to 5, and then y from -4 to 4. And then our title this time is going to be y prime equals, now I'm getting crazy with the typing, so you don't have to, again, you don't have to worry about this, but e to the y. And there we go. Yep, okay, that should do it. Yeah, it didn't print, but that's okay. So this one, I mean, it looks very nice, very, very well behaved, and that's probably because I chose to put the e to the y underneath. It's not actually that crazy of a differential equation. I mean, it's a crazy one in some sense, but the functions are pretty nice, right? So you can see that you have something that looks kind of like an equilibrium, but it looks like a curve, right? It looks kind of like a curve and not exactly like a horizontal line. And then everything's kind of tending toward this one. This looks like one sink over here, right? And they're moving, all these curves will be moving away from each other as you move to the left. Okay, so let me just try to fix that real quick. Yeah, it didn't work. Okay, so let's leave it there. Oh, I know what I need. There, beautiful. Okay, fix that. So let's go back to the notes and just look at this one curve. This one is the one that I want. So okay, so I'm back in my notebook here, and I've just imported the image of that slope field that we made with Sage. And so this was the one, right? So this was our differential equation that we just kind of made up on the fly. But it was y prime equals, if you multiply this out, this is 4 minus y squared. All right, and notice that this one is going to have two equilibriums, and they each correspond to each one of these factors, right? So this one gave us y equals 2, because that makes this whole derivative equal 0, right? And this one is going to give us y equals negative 2. And again, equilibrium meant that y prime is equal to 0, right? So our two equilibria are going to be this one, right? I don't know if I made that perfectly horizontal, but that one, and then this one. Okay? So these are our equilibria. I'll just write equilibrium number 1, equilibrium number 2. And all the other solutions are going to be curves, right, that have different behavior. So let's look at the behavior. So again, if we pick one, say we just start at this one, then as we move this way, this is going to have to get really steep, right? And then it's going to very quickly kind of approach exponentially, like approach the asymptote right there. In the middle, look what's going to happen. So let's say we start here. Okay, as we move to the right, our curve is going to get, or a particle, if we think of it as a particle, is going to get pulled that way. As we move to the left, it's going this way, but then it's going to get pulled this way, right? So this is going to look like a arctange or something. It's going to be squeezed in between these two, and it should not be touching that right there. So I got too close right there. It shouldn't be touching, right? And then finally, down at the bottom, we're back to our exponential solutions, right? So this one's going to very quickly get sucked down that way, and then this way. And so we can see that that there are two equilibria, right? But the solutions to this equation, there's infinitely many. There's infinitely many here in each region, actually, right? But they have three distinct, different kinds of behavior. So three regions where the behavior is completely different from the other regions, and the equilibria kind of divide those up, right? So the equilibria separate the whole plane into regions where the differential equation solutions behave completely differently. All right, well, let's leave that here for this first lecture of our course, and we will pick up from here next time.